Thank you for joining us for this broadcast of Science and the Solar Eclipse. I'm your host, Gordon Dickson. Once again on the broadcast today, we are talking about the fascinating connection between science and the solar eclipse. We have noted that there are several solar eclipses coming up here very shortly, and they'll be across the world, and we're just trying to make a connection between those and a scientific understanding of those. So once again on the broadcast today, we have Dr. George Matzko with us. Dr. Matzko, thank you for joining us again.
Thank you.
I was telling someone about our conversations just the other day, and he asked me a question which I thought I would pass along to you. And that question is this: how have scientists correctly measured the temperature of the sun? And I thought it was such a great question, I thought I would pass that along to you.
Well, I think I'd ask him, how do thermometers work when they take your temperature, aim it at your forehead? We all remember that from COVID days, taking our temperature of our forehead. It's the same thing, basically. We're looking at what we call the black body spectrum. So let's think about this simply. If you take a shoebox, you paint it black on the inside, and you put a pinhole in it and measure the radiation coming out of that pinhole of the shoebox, we can tell what the temperature of the inside of that shoebox is based on the black body radiation. That's the radiation, the continuous spectrum of electromagnetic radiation given off by a complete black object. And we can look at the peak intensity of that radiation, and by fitting that to a theoretical black body radiation curve, we can determine the temperature of anything. The sun's photosphere, which is 5,500 degrees Celsius, or the temperature of a forehead, or the temperature of molten iron in an ironworks. We can determine those temperatures directly using the spectrum.
And that is really intriguing, because even in the 1890s, they were able to grasp that and understand how to measure the temperature that way.
That's right. They didn't understand it completely. They were, those who were thinking about it in sort of more of a traditional, Newtonian way, were thinking that the radiation curve should just keep going up. As you got more energetic radiation, it actually should continue to rise. But what we see is the black body radiation curve reaches a maximum and then falls off dramatically. And because of that, we're not bombarded by hard or very energetic UV or X-rays or gamma rays in that highest energy part of the curve. And so that allows life to exist on the Earth. So it actually has a maximum that drops off. And so by measuring that maximum, we can find the temperature of anything remotely. It can be our sun, it can be a distant star, many, many light years away. And we can tell what the temperature is based on the black body radiation curve.
It really is wonderful to hear you describe so much of what we think is just ordinary and routine with a scientific underpinning and understanding what is really at work and how scientists have learned how to measure those things. Let's talk a little bit about the stability of the sun. I think it was during a solar eclipse that Aristotle said, I think it's a gaseous ball. And that's the way most of us today think about the sun, as a hot ball of gas. But when you think about the stability of the sun and the sun's intense gravity, how does it maintain its stability?
So you have a large gravitational force. The sun's enormous mass generates a powerful gravitational force. If indeed you think of gravity as a force, but that's a whole other issue. We'll talk about that later, I'm sure. That acts to pull the material inward. And that's responsible for compressing the sun's gas and plasma, creating high pressures and temperatures at the core. But within the sun's core, you have nuclear fusion reactions going on continuously. They're releasing vast amounts of energy in the form of electromagnetic radiation, primarily in the form of gamma rays. And this radiation exerts an outward pressure on the surrounding material and pushes against the force of gravity. So the stability of the sun really it results from a balance between these two forces. So you have a hydrostatic equilibrium. At any given point within the sun, the inward gravitational force is precisely balanced by the outward pressure exerted by the radiation generated in the core. And they call this balance a hydrostatic equilibrium. It ensures that the sun maintains its spherical shape, prevents collapse under its own gravity. I know you have already referred to the sun as being a perfect sphere, and it's one of the most perfect spheres in our solar system because of this hydrostatic equilibrium. We also have energy transport. In addition to maintaining stability, the balance between gravity and radiation pressure also facilitates the transport of energy from the sun's core to its surface. The energy generated by the nuclear fusion at the core gradually diffuses outward through radiation and convection processes, providing the sun with its luminosity and heat.
And what I've read and seen in various news articles, especially with some of the amazing telescopes they have now, are we've observed stars that were collapsing or have collapsed. And would that be because that equilibrium was not maintained?
That's right. So eventually a star is going to run out of fuel, or at least enough fuel to keep that delicate balance between gravitational forces pulling inward and radiation pushing outward. And so it's possible then for the star to collapse and go supernova and just completely blow up.
And so I think you referred a few moments ago to this radiation pressure. How does that work exactly? And what do we know about radiation, the pressure exerted by radiation in the universe around us?
So you have thermal pressure, the pressure arising from the random motion of particles within a substance, such a gas or a plasma. Particles move and collide with each other. They exert a pressure on the surrounding material. In astrophysical context, the thermal pressure is typically dominant in the outer layers of stars, where temperatures are lower and nuclear fusion reactions are less intense, contributes to supporting the outer layers against the inward pull of gravity. Thermal pressure is described by a very familiar law called the ideal gas law that everyone learns in high school in chemistry or physics. P equals nRT. So P is the pressure, N's the number of particles, number density of particles, what we call the number of moles. R is the gas constant, and T is the temperature. So we can infer the thermal pressure in stellar atmospheres and outer layers from spectroscopic observations, and that provides us information about the temperature of the gas and the density of the gas, and we can just plug that into the ideal gas law. Then there's the radiation pressure. Radiation pressure arises from the momentum carried by photons, which are particles of light as they interact with matter. When photons are absorbed or scattered by matter, they impart momentum to it, resulting in a pressure exerted by the radiation. So this equation is especially important in the cores of stars. And it is the radiation pressure, P, is equal to a formula that includes the Stefan-Boltzmann constant, the speed of light, and the temperature. And so the speed of light is part of this radiation pressure. Again, it's a very large number. So we can infer the radiation pressure from the analysis of spectral lines, studies of dynamics of glass clouds and dust grains and radiation fields, and theoretical models of stellar interiors and radiation transport.
I'm wondering if this is connected to what most of us learned in our science classes in high school, or if it's an apples and oranges comparison that I'm trying to draw here. But I remember we talked about how heat is conveyed. I remember there was conduction and convection, but also radiation. I still remember our science teacher standing by a window on a cold day and said, why is it that you can reach out and touch the glass and it's cold, and you know it's cold outside, but you can feel the radiant heat of the sun on your skin. Is that in any way connected to what we're talking about here?
Yeah, did you ever, I think when I was growing up in the 1950s, gets my age away, we had radiometers. They're little glass bulbs,
Mm-hmm.
like little light bulbs, and they had some veins in it,
Mm-hmm.
and you put it on your kitchen shelf, and the light would come in the window, and it would spin around. So it was made of. It had a black coated surface and a silver coated surface on these veins, and it would cause it to spin around when the sunlight would hit it. So what's happening here is the light from the sun is hitting the black surface, causing it to heat up and causing the vein to move around. So we can actually see the movement based on the heat from the sun.
And would that be radiation pressure that does that? Is that the right term for it?
You can think of it as radiation pressure, but primarily it's just the heating of the sun's the infrared from the sun hitting the black surface and causing it to heat up.
I see.
And therefore the molecules of air next to that vein heating up and pushing it around. So that's not exactly what we're talking about here.
I see.
The radiation pressure, we're talking about something that really is occurring inside the sun itself, and which is based on the momentum of the light photons. So no, I guess I should say no, it's different than that.
I see. This has been much in the popular news and popular speculation. People have talked about fear that the sun is collapsing or burning out or other things like that. And once again, it just shows us the Lord's amazing provision for us in what he has provided for us in what we call the sun. As you said, intense gravitation, but still upheld by both thermal and radiation pressure so that it maintains its stability. Another remarkable way the Lord provides for us, isn't it?
Secular scientists who, don't think about what the Lord has done would say that what's going to happen to our sun is that it's gone through different stages of stellar evolution over deep time. And what it would happen is the sun would continue as it loses mass, get larger and larger and larger, become what they call a red giant. Mm-hmm. And the sun would actually envelop the Earth. The sun would become so large it would actually increase in size beyond the orbit of the Earth, and the Earth would be swallowed up by it. So that's what they see happening in the future. Before the sun would collapse and become supernova, you'd actually have this red giant form, and that would extinguish life on the Earth. But they're talking about billions and billions of years in the future.
Mm-hmm. Once again, it just shows us how God has provided for us in remarkable ways. Dr. Matzko, thank you again for wonderful explanations today. I look forward to our next discussion as well.
Thank you. Looking forward to it.
Thank you again for joining us for these series of conversations with Dr. George Matzko. He can be reached at his website, georgematzko.com. That's GeorgeMatzko.com. The Matzko Science Ambassadors. These broadcasts are brought to you by LiveServeLead.com. Live, Serve, Lead, helping others succeed.